Right, so today is going to be the last lecture in what's essentially been a sequence of lectures in which over the last few weeks we've been looking at subsets of natural numbers and their computability properties. The title of today's lecture, it's just fitting in where we are, where we're going today on what we've been doing. And then we were doing that up to 2 weeks ago, and then last week we looked at also considering these subsets as indices for sets of computable functions and the computability properties of sets of functions. When is a set of computable functions, when can we decide whether or not a property holds of computable functions or semi-decide property holds of computable functions. So we've been going in that sort of direction, but thinking about subsets of the natural numbers, essentially we've so far got a classification of subsets into 3 different categories. So we've seen subsets that are, so the best computability property we can get is decidable, or another word for that is computable when we're talking about subsets of the natural numbers. So we all know what that means by this stage, this decision procedure that tells us if a number belongs to the set or not. The next best category is semi-decidable, or computably enumerable, as we're also calling them. So those that we have, as we know by this stage in the course, those that we have a test that will tell us positively if a number belongs to the set, but won't give us any information if it doesn't belong to the set. And then the third category is those subsets that are neither computably enumerable nor computable. So these are the sets that are not semi-decidable. And what we're going to do today is we're going to see that sets can be not semi-decidable in some interesting ways. So it's not, not being semi-decidable is certainly a negative property in that you don't have the ability to test, at least in this halfway of testing, just test for positive membership. We don't have the ability even to test for positive membership of the set. But nonetheless, sets can be not semi-decidable in different ways. And one of those ways is actually very interesting. And in fact, the way this lecture is going to be structured is, in the first hour, I'm going to introduce this way that's very interesting, but you might not fully appreciate why it's very interesting in the first hour of the lecture. It'll be appreciated more why it's very interesting when we consider an application of it, and that's going to be the second hour of the lecture. But in order to do the application, we really need to do the theory first. So although in the first hour of the lecture, you're going to see what I'm going to tell you is an interesting way of not being semi-decidable, you might think, well, that doesn't look very interesting to me. At least hold your breath until the second hour of the lecture, because in the second hour of the lecture, we will see an application of the concept. So the other thing to say is, I've already said this is essentially the last in this group of lectures that are culminating today. From next week, as I told you last week, we're going to switch to another computability model. We're going to kind of go back to the basics of Turing machines and start a new topic. Okay. So we're going to look at sets that are not semi-decidable and find an interesting way in which sets might not be semi-decidable. So let's consider, well, I'm going to use more of the computably enumerable terminology. So let's consider an arbitrary set of natural numbers. So this box here is a set of natural numbers, and let A be some subset of it. We're going to put a kind of jagged edge around A, which is supposed to indicate that it's maybe not a very nice, very well behaved set. It's got a kind of awkward boundary, so it's hard to tell whether a number belongs to the set or is outside the set. So here we have A, and here we have its complement. So if A is not computably enumerable, well, what does that mean? Well, one consequence of that, which is in fact equivalent to being not computably enumerable, is if we consider any one of our computably enumerable sets as enumerated, and remember we're enumerating the computably enumerable set, sorry, that should be W2. Enumerating the computably enumerable sets as the domains of the partial computable function, the zero index partial computable function, the one index, and so on. This is our enumeration of the computably enumerable set. For any computably enumerable set, a WE say, suppose we find such a WE, and for that index E, the computably enumerable set happens to be a subset of A. That's not going to happen for all indices, because I mean some of these, infinitely many of these indices will actually give W sub E is the whole set of natural numbers, for example. If we get all the computably enumerable sets infinitely often in this listing. But if we have such an index E such that the computably enumerable set is its indexes, which is the domain of the E index partial computable function, is a subset of A. Well, if A is not computably enumerable, that of course means that there exists some X. I mean, it's a triviality, but there exists some X that's in A but outside of WE. So there exists some X that belongs to the set A with WE. This is the set difference operation, so with the elements of WE. I'm missing. So if A, and I missed the condition here, which is, and if WE is a necessarily computably enumerable subset of A, then there exists an X such that, right, there exists an X that belongs to A and is outside WE. Okay, so that's a triviality. And in fact, this property here that for any such WE there exists an X outside it is actually obviously equivalent to the non-computable enumerability of the set A. This way of thinking actually leads quite naturally to a strengthening of not being computably enumerable, which is saying, well, can we be not computably enumerable in a sort of constructive way, which is that in such a way that we have a program that, given an E, for which WE is a subset of A, will give us back such an X. In other words, can we find sets such that we have a computable function that will take us from an E of this form to an element X that's outside of A, that's in A but outside of the main set WE. And we're simply going to put that in a definition. So move the camera. The definition is a notion called productive. So a subset A of natural numbers, a set of natural numbers is productive if there exists a computable function, going to ask for it to be total, so we always get an answer. One can weaken the notion in an interesting way, not asking for totality, but we'll stick with the standard notion in which we do ask for this function to be total. So if there exists a total computable function, and now I need to refer to my notes to remember, because I do want to be consistent, I want to remember what letter I call it in the notes. G, very anonymous letter for a function. So it's a total computable function on natural numbers, such that for any natural number E, if in the case that E is the index of a computably enumerable subset, a computably enumerable set, it is a subset of A, then our function G applied to E will find us an element of A which was outside of that computably enumerable set. Okay? So we have a computable way of going for, we try to find a computably enumerable set that agrees with A, if you like, by giving it its index. And we have to at least, if it's going to agree with A, it has to at least be a subset. But we're always foiled because our computable function G will find us an element that we've omitted from our computably enumerable set. Okay? So, quite nice because this function G, however we try to capture A by a computably enumerable set, a function G gives us a way of actually finding out for ourselves, of discovering how we failed. Okay? Anyway, we're going to see a mathematical situation in which it's really important to have such a computable G in the second hour of the lecture. You might wonder, well, maybe it's a bit much to hope for, but we can find such a computable function G which will always find us an element that we omitted. But it's not, so let's give an example, an immediate example of such a productive set. And the proposition is that complement of the halting set K is productive. So remember, we showed that the halting set K is computably enumerable, but that it's not computable. Because it's not computable, its complement, that was how we discovered that its complement is not computably enumerable, because if it and its complement were both computably enumerable, then it would be computable. So it's computable, we already know that this set here, the complement of K is not computably enumerable. But it's not just not computably enumerable, but it's not computably enumerable in this stronger way that we can even find the elements that we leave out when we try to find a computably enumerable approximation of the set, and we can find those in a computable way. So let's prove this. It's a very short proof. I'm going to tell you at the start what the required function, computable function G is, and it's actually just the identity function. So when we show that the function, the identity function so we'll still call it G, GD, G max G to itself does the required job. Okay. So So maybe before carrying on, I'll remind you what the set K is. So recall K was the set of numbers E, such that the E index computable function applied to the number E was defined rather than under. So this is the E index computable function is defined on its own index given as an argument. Don't need to talk you through this again because we considered this a few lectures ago. But notice that another way of writing this is the set of all numbers E such that, well, this says that E is in the number E, the argument here is in the domain of the E index computable function. So another way of writing this is that E belongs to the set WE, set of numbers that belong to their own the computably enumerable set they index. Okay. So now we want to show that this identity function does the job. So let's suppose that WE is a subset of the complement set K. Suppose WE is a subset of the complement set of K. And what we need to show is that G of E, that's E itself, we need to show that E belongs to the set we're showing is productive, that's the complement of K with WE with the E index computed enumerable set taken away from it. So there are two things to show: that E belongs to the complement of K and that E is outside of WE. So let's first assume for contradiction that E belongs to K. So suppose for contradiction that E belongs to K. So then if E belongs to K, then E belongs to WE. But because we've assumed that WE is a subset of the complement of K, but since WE is a subset of the complement of K, E belongs to the complement of K. So on the assumption that E belongs to K, we've shown that E belongs to the complement of K, so that's a contradiction. Okay, so there is a contradiction that E belongs to K, so therefore, indeed, for these three dots is an English way of writing therefore, indeed, E belongs to K. But if E belongs to K, then by the definition of K, therefore, indeed, E belongs to So it's a contradiction that E belongs to K, so therefore indeed E belongs to the complement of K, sorry. So E belongs to the complement of K by the definition of K. By the definition of K, these in the complement, E does not belong, E does not satisfy the membership condition for K, so E is outside of WE. As indeed, we've shown what we need to show, that E belongs to the complement of K that is outside of WE. That is, E belongs to the complement of K that is outside of WE as required. Okay. Right, good. So The complement of K is one such set. And actually, to then show that other sets are productive, because what's going to be useful for the application is not that this set is productive, but some nicely defined mathematical set is productive. It's going to be, then the fact that it's productive is going to give us some very nice information. We need a tool to show that other sets are productive. And a good tool for that is to use the tool of reductions that we introduced last week. And we're going to see that reductions allow us to transfer the reduced productivity from the complement of K to other sets. So we're only going to use total reductions. So remember from last week, a total reduction, and I'm not going to say total in this lecture, all reductions are total from A, which is a subset of N, to B, is a computable total function. I won't write the total, just write the total arrow, such that all N belongs to A, if and only if f of N belongs to B. So we can reduce questions about membership of A, questions about membership of B, using the total function f. So that we had last week, and I'm going to give a bis to the reduction lemma. No, bis in Italian at least is at the end of the concert. If you want a little bit more, an encore or a French or a bis in Italian. So just in case you were asking for more from the reduction lemma, you weren't satisfied with the reduction lemma from last week, you were clamoring for more, then here it is. Did I? So the additional property is that if a productive set reducible to B, and B is also productive. Well, this might look a little bit different from the reduction lemmas we had last week. Reduction lemmas we had last week were about transferring properties, computability properties from B to computability properties of A. So we had, if B is computable, then A, we've got that we had if A is reducible to B, then if B is computable, then A is computable, and if B is computably enumerable, then A is computably enumerable. But if we think about that with computable enumerability, we've got that if B is computably enumerable, then A is computably enumerable. So the contrapositive is that if you've got a reduction from A to B, if A is not computably enumerable, then B is not computably enumerable. And that's the statement that's related to this, because productivity is a strengthening of being not computably enumerable. So having a reduction preserves non-computable enumerability in the forward direction from A to B. And it doesn't just do that, it even preserves the stronger property of productivity, which is not computably enumerable in this stronger way that we have this computable function that finds us the elements that we left out of any attempted enumeration of the set. Okay, so we're going to prove this. Maybe I'll start down at the bottom. So let F be a reduction from A to B. So what we're going to do is we're going to observe that the partial function below is computable. And this maps, it's a function in two arguments, takes an E and an X, and it maps us, it takes the E indexed partial recursive function and applies it to f of x. Okay, this is a partial function in two arguments. It's computable because using the universal partial computable function, this is phi of, which is the universal function of E as its first argument, f of x as its second argument. Okay. So, as you may be getting used to now by the lectures and the exercise classes, when you've got the two argument function, you turn it into a one argument function using the SMN theorem. So by the SMN theorem, there is a computable total function such that, I'll just write S dot D on the right here, such that if we apply H to E, it gives us an index for this, the action of this function in the right-hand argument, in the argument x. So phi H being applied to x is the same as phi sub E of x. Or another way of writing that is that phi sub H of E is the partial function we get by composing f with the partial function phi of E. There's the partial function phi of E composed with f. Okay, so with these basic observations, we still need to prove what we want to prove, which is that if A is productive, then B is productive. So let's just put this, I'll put the assumptions about the names of things here. So suppose G, which is again the total function of natural numbers, witnesses, that means it is the function associated with the property of A being productive. So witnesses the productivity of A. So what we're going to do, we want to show that B is productive. We're going to show that its productivity is witnessed by the function that we get by composing the three functions we've got at hand together. So we're going to show that the composition F composed with G composed with H, the composite of three total functions, witnesses the productivity of B. So in other words, we suppose that WE is a subset of B. And we need to show that F, G, H of E belongs to B, but is outside of W E. So if WE, well, maybe I'll go on to the other board. I think there's needs to be on the other board here. Okay, so WE is a subset of B. So you saw the comment. I should indeed, thank you very much. The other thing I'm dying to do is open the window, but I think given that, I don't know how you feel about the air in the room. I mean, either the window or the door needs to be opened, but given that we're quite close to the break time, I think we might as well. I don't want to fiddle about with the window now, but I shall open it during the break. Right, so WE is a subset of B. So in other words, so WE is the domain of the E-indexed partial computable function, where we have the domain of phi sub E is a subset of B. That's the same as WE is a subset of B. Since F reduces A to B, that means that anything in the domain of E belongs to B. So by the property of the reduction here, that F of something belongs to B if and only if the number, the thing itself belongs to A, we have but the domain of, we compose by E with F, that belongs to F, subset of A. In other words, the domain of phi HE, because H of E was phi E composed of that, is a subset of A. Which is the same thing as saying the domain of the HE indexed computable partial function is the definition of W sub HE. So W of HE is a subset of A. So find the productivity of A. We've got a computably enumerable approximation to A. Find the productivity of A if we apply G to H of E. G of H of E belongs to A, but is outside that computable approximation that we had. Okay, so G of H of E belongs to A. So again, by the definition of the reduction, f of g of h of e belongs to B. By the reduction again, f of g of h of e belongs to B. But moreover, if g of h of e is in the domain of h of e, well then f of it is necessarily in the domain of sorry, g of h of e is outside the domain of h of e, so f of it is outside the domain of phi of e, because phi of e right, I'll think about this. So anyway, this is what we want. So let's just think about it. Hopefully somebody can see it. I saw it half an hour ago. It's amazing how one can get confused. I mean, it's easy, but I just need to see it. So anyway, that is just to finish. I mean, it's obvious. So is it obvious? I mean, it's obvious if you think about it the right way. But it's always when points like this arise that I really regret that I'm recording lectures. So, but anyway, it's too late now. So let's work it out, and then we'll have the break. But it's really trivial. So we've got g of h of e does not belong to w h of e. So f of g of h of e, I'm claiming does not belong to the domain of phi e. So this is what we want. So suppose, and we're going to prove the contrapositive. So suppose f of g of h of e belongs to the domain of phi of e. But then, if it belongs to the domain of phi of e, then if we then it belongs to the domain phi of e well then of course g of h of e belongs to the domain of phi e composed with that. Right, obviously, because if we apply f to this, then we've got something in the domain of phi of e, and this is the total function. And this, and phi of e composed with that is phi of h of e, so g of h of e belongs to the domain of phi h of e, which is w h of e. So we proved the upwards implication, and therefore we get the downwards implication. Anyway, good. That's a relief. So it's I mean, I started very late, but so it's now only very slightly late break. So I I suggest we have a break until 15:15. We're going to do something completely different in the next hour, less technical, and I'm going to open the windows as well, if that's okay with everyone. I'll pause the. Right. Okay, so I promised you that the second hour would be very different from the first hour. But actually, before starting on the second hour proper, I just want to finish off a little bit the study of these productive sets that we were looking at, just with a few more actual concrete examples of productive sets. So we've got this reduction lemma that tells us we can, if we reduce a productive set to another set, then that other set is again productive. We can use this to give a stronger version of this Rice's theorem from last week. So remember, last week we had Rice's theorem, which said that suppose B is any set of unary computable partial functions. So last week we had that B is always undecidable, except in the case that B is empty or the set of all computable functions. Then we're going to have a result that's actually a little bit stronger. So suppose it is such that remember this was the everywhere undefined partial function, belongs to B, but B is again, so this means B is non-empty, but it particularly contains the everywhere undefined partial function, and B is not the set of all computable functions. So by Rice's theorem, we know that the set of, we know that B is not decidable, that is the set of indices for B is not computable. What we're going to get today is that it's not just not computable, it's also not computably enumerable, and it's not even just not computably enumerable, it's even not computably enumerable in the strong sense that it's productive. We have this witness of it not being computably enumerable. So then, the set of indices of the functions in B, as defined last week. So just all those numbers E that by B belong to the set B. Number T is the set of computable, so unary computable partial functions. So this set of indices is productive. And I'm just going to tell you the reason without going through the details, but all the details have essentially been given. So the proof is that last week's proof of Rice's theorem actually establishes reduction from complement of the halting set K to IB. Since we've shown that the complement of the halting set is productive, and we've got this of the reduction lemma, IB is productive. So therefore, IB, the set of indices of functions in B, is productive by the reduction lemma. I'll just put RL this, and because a complement is productive. And that's it. I mean, you have to check that last week's proof of Rice's theorem indeed does this. That's almost immediate from what's written there, except, so just to put in blue, you have to be a little bit careful, because if you look at last week's proof of Rice's theorem, we assumed without loss of generality that the everywhere undefined function did not belong to B. And now it's actually essential for this result that the everywhere undefined function does belong to B. So you need to follow the alternative branch of the without loss of generality, which is explained in the notes at the time of, so you don't follow the same branch of without loss of generality, but the alternative branch of the without loss of generality to get this. And when you do this, you'll actually find that you get a reduction from K to the complement of I of B. But a reduction from K to the complement of I of B is the same thing as a reduction from the complement of K to I of B. So those are the slight qualifications, but basically this holds. So the interesting point about this is that if the consequence of this is that whenever you have a set of computable partial functions, if it's a non-trivial set, it doesn't contain every computable partial function, but it contains the empty partial function, then, well, it's productive, so it's a fortiori not computably enumerable. And in fact, we could have verified that part, not the productivity, because that's new, but that part that is not computably enumerable, that's a consequence of Rice's theorem. So a consequence of Rice's, sorry, not Rice's theorem, the Rice-Shapiro theorem. So a consequence of the Rice-Shapiro theorem is that if you have a computably enumerable set of computable partial functions and it contains the empty partial function, then it is the whole set of partial functions. And that, I think, is going to be an exercise in today's exercise class. So there's a network of results that have kind of connections between them. But anyway, this statement is now that we've got today is a simple consequence of Rice's theorem in the way that I've outlined here, and is a nice, basically very, very many sets of indices of functions are productive. So before going on, there's one last thing, and then we're going to move to the more relaxed topic, which is the motivation, which is a motivating application for all this. But before moving on, I just want to have one more definition. So we've been talking about sets that are, come on. Sets that fail to be computably enumerable in a strong way. There's a kind of interesting related concept about computably enumerable sets, which is the following. We say a set A of natural numbers is created. So there's creative terminology going on in this usability theory. There are lots of strange names for things. Productive is not so unreasonable a name because you're sort of producing an element that's doing something. Anyway, we say that is creative if it is computably enumerable and its complement is productive. So just as the productive set is one that fails to be computably enumerable in a strong way, remember, a set is computable if and only if it's computably enumerable and its complement is also computably enumerable. So computable if and only if it and its complement are both computably enumerable. So if a set fails to be, is computably enumerable but is not computable, then it is computably enumerable, but its complement is not. So in that sense, here we're saying, I am computably enumerable, but my complement is not just not computably enumerable, but moreover, not computably enumerable in a strong way. So the idea of that, those lots of words, but basically creative is kind of computably enumerable, but not computable in a strong way. So computably enumerable, but in a strong way, not computable. think about. And just an observation, proposition, halting set K is creative. We've seen that it's computably enumerable, we've seen that its complement is productive. And secondly, another result related to Rice's theorem, which is if we've got, again, a set of computable partial functions, sorry, these are proper subset, so it's a non-trivial set of computable partial functions, and its set of indices is computably enumerable. So we saw last week the Rice's theorem, which tells us some properties are satisfied for any function in it. There's some finite subfunction of that that kind of determines membership of the set. But the result I want to mention now is that if the index set is computably enumerable, then it is creative. So the point here is that any set of computable partial functions that fails to be that is semi-decidable, that means its index set is computably enumerable. Actually, that index set fails to be computable in a strong way, and its complement is productive. Right, good. So that's the technical bit out of the way. And now let's maybe clean the boards. So what I want to do now for the rest of this part is look at what I think is a really nice application in the sense of these ideas, or at least a topic in which these ideas provide a very productive, a very useful way of thinking about what's happening, and that's related to Gödel's theorem in logic, Gödel's incompleteness theorem. Now, Gödel's incompleteness theorem is quite an advanced topic of logic, but actually, for what we need to discuss today, we don't need to know any advanced logic to be able to discuss this. And it's essentially that the notion of productivity applies to the concept of mathematical truth. That's essentially what I'm going to explain to you. The concept of mathematical truth is clearly a very important concept, because essentially the whole of mathematics, or a lot of mathematics, is about establishing mathematical truths. At least one hopes it is. And it looks like it's, that sounds almost like a philosophical topic, mathematical truth. So what does it have to do with these very technical concepts in computability theory? Well, to talk about that, I do need to introduce you to a little bit of logic, but nothing very difficult. What we do need, so we're going to look at mathematical truths. But regarding arithmetic, which is like number theory, for which the notion of truth is less controversial than in more general mathematical subjects like set theory or something like that, where the very notion of truth is a bit controversial. Number theory is not very controversial, what it means for something to be true. So the idea in logic is that we want to, well, one of the important ideas of logic is to look at what are called formal languages, which are precisely defined languages for stating mathematical properties. And in particular, we're going to look at what are called the first order formulas. in the language of arithmetic, given by firstly, the idea of first order formulas is they're going to be formal strings of symbols that have some meaning attached to them, and the meaning is a mathematical statement. And the first such formal string of symbols we're going to look at are equations between polynomials that have natural number coefficients. So P1 equals P2 is a formula in first order arithmetic where P1 and P2 are multivariate polynomials. So multivariate means it may have any finite number of variables. Multivariate polynomials with natural number coefficients. So that's one class of first order formulas. Now, first order formulas state properties. So this states the property this polynomial equals this polynomial. That property will sometimes be true, sometimes false. You know, that's the nature of properties. They're sometimes true, sometimes false. But once you've got properties, you can combine them using the logical connectives, such as negation, conjunction, disjunction, implication, and so on. So we're going to allow ourselves to build formulas using the logical connectives. So we give ourselves the negation of a statement phi, where phi is a first order formula. So you can already construct phi as a first order formula. We can also construct not phi, then we can construct not phi, which is of course equivalent to phi, as long as one agrees with classical logic, as it's called. So, for example, combining negation with equality, we can say that two polynomials are not equal. We'll also give ourselves conjunction, disjunction, implication. So these are three different things. So this is and, or this is implies. Phi implies psi. Conjunction, disjunction, implication. So if phi and psi are formulas, I just write formulas rather than first order formulas. And lastly, we've got quantifiers, which is for all x phi and exists x phi. So if phi is a formula and x is a variable. And the idea of the language of arithmetic is that we're talking about properties of natural numbers. So that's why we only have natural number coefficients in our polynomials. And for all x phi and exists x phi, we interpret as there for all natural numbers x phi holds, and there exists a natural number x such that phi holds. Okay? So the variables, this is to do with arithmetic, variables, the fact that we talk about arithmetic rather than say set theory or something else, variables are understood as ranging over natural numbers. So just to check that to understand what we're doing, I'm going to give you some concrete examples. I'm not going to take very long over it because those of you who've done a degree here will have done Mathematica in Logica in the first year. Logika množica, that's what I mean. In the first year, so obviously that'll be fresh in your memory. And probably most people have seen similar things in the past. But I mean, the idea is that formulas express properties of natural numbers. And the thing is, I have a number of courses where I've got a logic course, which will take place next semester. That's going to be a theory course on logic. But I have a number of courses that touch on logic in one or two things. I always give the same introduction, but because these examples seem sort of very easy ones to relate to, I'm going to give the same examples I always give, so forgive me if you've seen them before. But formulas allow us to express properties of natural numbers. So, for example, consider the property that there exists a z such that x plus z equals y. So this is an equation between two multivariate polynomials, very simple polynomials. And they can be quantifying over the z. So there's not. So this formula is expecting a property, a relationship between x and y. It's saying x and y are natural numbers, and it's saying there exists another natural number z such that y is x plus z. So can somebody tell me what this property is, in other words? So this expresses the property what relationship between x and y holds for y is x is smaller than y. So x is less than or equal because 0 is a natural number in today, and I mean, school mathematics it's not, but in university mathematics and beyond it is. Expressing the property that x is less than or equal to y. Okay, so let's do something a bit more interesting. So now we've got less than equals, we can use the formula for less than equals, we can use it in the case of 2. And let's say 2 is less than equal to z. So that, if you want, exists the w such that z plus w, such that 2 plus w equals z. That would be that. I'm just writing shorthand. Obviously, it doesn't matter what names we call variables. The 2 is less than equal to z, and for all x, for all y, z equals x times y implies x equals 1 or y equals 1. So this is expressed as a property. Because we're quantifying over the x and y, it doesn't express the property of x and y, it expresses the property of z, which is the only variable that we don't quantify over. And what does this express the property? The z is a prime number. Very good. Okay, so we see how formulas express properties, and we also notice that they express properties of those variables that we don't quantify over. So what if we quantify over all variables in a formula? Well, then we're simply expressing properties that are either propositions, if you like, that are either true or false. And these formulas are called sentences. So a formula is a sentence if all variables are quantified. Sentences express propositions that are either true or false. So let's have a look at some examples of sentences. So this one I'm writing this formula. We may change the name of the variable we're quantifying over if we need to. It expresses x is equal to y. This formula will express as prime z. So here's a formula in which we quantify over all variables. So for all x, for all natural numbers x, there exists a natural number y, such that x is less than or equal to y, and prime y, and y is prime. Okay. So is this true or false? And what does it say? There are infinite many prime numbers, which of course is true. So this expresses the true property. That's infinitely many in prime numbers. So what about this one? All x, there exists a y, such that x is less than or equal to y, and prime y, and prime y plus 2. So what does this express? There are infinitely many what are called twin primes, primes that have a distance 2 between them. And as you at the back said, this is famously known as the twin prime conjecture, because nobody knows, well, I was going to say nobody knows whether it's true or false. I mean, people are absolutely sure it's true, but nobody has been able to prove it. Massive progress towards this was made in the previous decade. So the first in 2013, I think it was, Sue, I think it was called, proved that there exists some fixed number that you can replace 2 with here, such that this formula holds. So that there is a gap between primes that occurs infinitely often. So that was in 2013, and subsequent to that, that gap has been reduced from a huge number down to something in the, I don't know, hundreds or thousands or something like that. I'm not quite sure what the current level is, but I really don't know. So anyway, it's not yet it's 2, which is what people are aiming for. But anyway, I mean, hopefully you'll agree this is, one believes in properties of natural numbers of this simple form are either true or false. It's just a matter of the mathematicians to discover, try to understand what truth is and to prove that. And examples such as this point to that understanding the nature of truth is tricky. Mathematics is not an easy task. And the point I'm going to try to convey to you now is that computability theory can actually give us some positive information about the way in which mathematics is not an easy task. Let's move the camera. Oh, maybe I keep that. So the first thing we're going to observe is that the formulas can be represented perfectly easily as strings of symbols over some finite alphabet. I mean, that's essentially how we write them on the board. So formulas should be FOR. Formulas can be represented as words over a finite alphabet. And we've done enough of these kind of encodings that I don't need to go into considering details about how one might do that. Now, there is a slightly tricky point because the rules for being a formula being well formed, it means you need to combine the symbols in a particularly good way. You need to follow the rules. So not any word over the alphabet is going to give us a formula, but nevertheless, the rules are sufficiently simple that given a string of symbols, I think you can believe me that there's an algorithm that will look at a string of symbols and decide whether or not it represents a formula or not. I mean, such a thing in computer science, this task is known as parsing. You're given a word, that's a string of symbols, and you parse it to get the struct to see that it's appropriate, that it conforms to the grammar of the language that you're generating, and you parse it to check that it's, when you write a computer program, it first gets parsed to see if it's textually a legitimate computer program. It's the same thing here. We can parse a string of symbols to see if it's a formula. So it is decidable if a word represents a formula or not. And then sentences are particular formulas that have this extra condition that all variables are quantified. And again, you can perfectly well test that. You can look at the formula, look at all the variables in it, and check that they're all inside the scope of the quantifier. So it is also decidable if a word represents a sentence. And here I'm talking about representing formulas as words over a finite alphabet. That's kind of how we write them on the board. But in computability theory, we've seen that everything can be coded as natural numbers. So words over finite alphabets can be ultimately encoded as natural numbers. So let's now convert to natural numbers just for convenience. So alternatively, we have decidable subsets cent, which is a subset of the set of formulas, which is a subset of the natural numbers. I mean, if one's really clever, one might be able to encode formulas in such a way that every natural number represents a formula. So that's why I allow this to be an equals here. Probably wouldn't be under a normal encoding. So this is numbers encoding sentences. numbers encoding formulas. And then, of course, we've got the set of sentences. We also have another set, which is a set that mathematicians are trying to discover. True, which is the set of true sentences. Well, actually, maybe I'll put this on in the next column because I'm running out of space to elaborate things. So that also allows me to say these are decidable, that is a subset of natural numbers. Another word for decidable is computable. These are computable subsets. So we can define true to be a set of numbers n such that there exists, well, such that n belongs to sentences and the sentence by n encoded by n is true. Those numbers that encode, here we have all numbers that encode sentences, those numbers that encode sentences and for which the sentence that they encode happens to be true. So can anyone guess what the difference is between true and these two sets, or what a difference is? Right, it's not decidable, very good. Anything else? Well, it's not decidable, so it's certainly a subset of a set of sentences. It is decidable, it's not decidable, so it can't be the whole set, so it must be strictly smaller. So yes, that's true. Anything else? Does anyone want to be more bold?
Probably not seen.
It's also not computably enumerable.
So it's like just being
Sorry?
it's like it's not seen, but it's the one thing that we can find there.
Very good. So theorem. And this is very closely related to Gödel's first incompleteness theorem. It's not exactly the same. In some ways it's stronger, in some ways it's weaker. But it's a very good theorem in its own right, and I think we should, basically Gödel gets kind of credit for it. And the theorem is that true is productive. It's not computable, it's not computably enumerable, and it's worse than not computably enumerable, which is that it's not computably enumerable in a strong way. But is that really worse? So I'm going to a little bit argue that in some ways it's better to know that it's productive than it would be if it were just not computably enumerable. It's actually good. I mean, given that it's not computably enumerable, it's actually useful to know that it's productive. So maybe I can squeeze this into the remaining time for this hour. And what I want to do is consider how useful it would be to be able to computably enumerate mathematical truths. We might have many ways of doing that. And in fact, all these ways, you try to do them in practice. So it's kind of the toolkit of the mathematician, so to speak. So ways we might want to enumerate, computably enumerate, I mean, mathematical truth. That's the mathematical truths. We don't need mathematical truth, in fact, the whole of mathematical truth, at least some mathematical truths. So one is something which we'll call a proof checker. In a sense, this is the way that the standard mathematician operates, but it's now getting to the stage that it's being automated on a computer. And this is, we have a program that takes as input a sentence by and a claimed proof of pi. Let's call the proof pi because pi is a p. The proof. And the program, the idea is that you give a proof, a formal proof, according to following from some fixed set of axioms and following for some known rules for constructing a proof. We should be able to provide a computer program that will check that we've correctly followed the rules and either tell us yes or no. And the program outputs either yes, this is a correct proof, or no, an incorrect proof. Okay. If it's an incorrect proof, it's not saying it's false, it's just saying that the mathematician failed to provide a correct proof for it. So such programs actually exist and can be, one can perfectly well provide such things using various known axiom systems for mathematics for the test. So these are called proof checkers. And this is essentially giving us that the outputs of the programs for which the sentences for which the program is able to output yes are a computably enumerable set. We have the phi such that there exists the phi such that the program outputs yes on inputs phi and pi is computably enumerable. Because this is programming outputting yes, that's a decidable property. And so here we've got a decidable property in two arguments, and we're looking at what happens so if there exists, given one argument, if there exists an argument that satisfies the other. So this was one of our models 2 lectures ago for computably enumerable subsets. We've got a decidable set of pairs of numbers. If you look at those numbers for which there exists a number that paired with it puts it in the decidable set, those are the computably enumerable set. So this is the computably, so whenever we have this, the sentences by that one can give proof to are necessarily computably enumerable. We of course want the program to be correct, so we want this to be a subset of truth. And the fact that this is productive means that when we have such a program, well, the program itself gives us, by just looking at the program, we can work out from that an index to this computably enumerable subset, applying the witness to productivity. That's going to give us a formula phi that is true, but does not have a proof in the system, for which we cannot give it a proof in the system. So the witness, so whenever we write a program with these meeting these conditions, the productivity, we've got a computable formula which we can essentially apply to that program, and that applying that computable formula, that computable function to the program, which is like an index to the computably enumerable set, gives us constructs for us a true sentence that our program is unable to verify. Okay, that's the idea. So I'm just going to say the same thing holds, and I'm going to list 3 more ways that we might try to enumerate mathematical truths, and all of them are going to suffer from the same defect. As soon as we have one, we can apply our computable function that we have from the productivity to the description we have of the program that we're looking at, and in doing so, we get automatically a sentence phi that's true, that is not, in this case, is not provable, but is not within the scope of the handle we got on mathematical truth. So the productivity means we have a way of actually finding, whenever we try to get a handle on mathematical truth, we have an effective way of finding something that we've missed out. It's very perplexing. Right, so let me just, we'll have a break very soon. I just want to list 3 other ways that we might want to enumerate mathematical truths, and now I need to go to my cheat sheet to remind myself what they are. Phew. What is it? Got lost there. So that's a proof checker. So a theorem prover. So in this case, I'm just going to say what the inputs are and what the outputs are. So in this case, the input is just a formula. And the idea of the proof checker is you rely on the mathematician to come up with the proof. The machine just verifies that it's a correct proof. In the case of the theorem prover, you're trying to be more automatic. So the input is the formula, and the output is eventually yes, well, a proof of the formula if one is found, a correct proof. So you don't rely on the mathematician to input a proof. Here the theorem prover is going to try to search to find a correct proof. It may, if you go into a loop, it may not produce anything if you give it something that's not true, but it's going to try and find a proof for you. Okay, and once again, in this case, if we have such a thing, we input a formula. If it outputs a proof, then that's like a semi-decision procedure saying, yes, we have a theorem here, so that's hopefully going to be a true statement. But this is like a semi-decision procedure, and it's giving us, and it's going to hold only on true statements. Because of that, it's going to give us the formulas on which it holds are going to be a computably enumerable subset of the set of truths. And therefore, again, by productivity, we can find a formula that we can recognize as being true that the theorem prover will not also. So something weak would be a truth verifier. in which the input is a formula. And the output is simply true if the program discovers that the formula is true. So there are other ways to establish truth other than finding a proof. And for some known classes of formulas, there is simply tests you can apply to see if the formula is true. If we have a program like this, again, this is a semi-decision procedure, it's going to have the same defects as before, but again, those statements that the program faults on, or outputs true on, will be some of the truths, but again, applying the productivity from a description of this program, we can find an index for the computably enumerable subset on which the program inputs true, and we can apply productivity to that and find ourselves a truth statement that the program doesn't fault on. Lastly, a truth enumerator. It's getting to, I wonder whether, so I didn't have any doubts when I wrote my notes about whether it's or or ER at the end of the word enumerator. I just looked at my note. This is the sort of thing that occasionally I have a mental block about. I just looked at my notes to check, but my handwriting is not readable. This now looks right to me. Anyway, truth enumerator is simply going to be a program that computes and computes and computes, and it outputs truths in sequence. Right, truth 1, truth 1, truth 2, truth 3, truth 4. So basically it goes on sort of discovering truths. It's like the whole body of mathematics being developed. So, when this is what mathematicians throughout history, you can view them as essentially producing a list in some sequence of truths that they're producing. So we can have a program that's doing that, outputting all these truths. But because this is then, we can view this as the range of a total computable function, then these formulas are output. For a given n, find the nth formula that's output in sequence. So the range of the total computable function. So again, by a couple of lectures ago, the images of total computable functions are computably enumerable sets. Again, this is a computably enumerable subset of truth. And from our program description, we apply the witness to productivity to it, and it will produce a formula that we can recognize as being true, that's not in the list of formulas that we produce. Okay, so the point is, this productivity gives us a way of saying from any approach we have of getting a handle on mathematical truth is bound to be incomplete. But it's incomplete in a very constructive way. But when we have such an approach, we can actually find, in a computable way from the description of what we're doing, we can find an actual truth that we omitted, which we can recognize as being true. Okay, so I hope that was, so I hope that gives you some perspective on this notion of productivity. It's now 10 past. I want to have only a short third part, so let's have a short break, so we'll start again at 10 past, sorry, not 10 past, that's now, it's 20 past, and I shall try to be quick in the third part. Okay. Okay, so in the notes, for this week, there's a little bit of an outline argument about
how that statement is proved that was mentioned in the second part, in the last part, namely that the set of true sentences has this productivity property. I don't want to go over that in the lecture. If you're interested in that, then have a look at it. The proof of that statement is not really an examinable, well, it's not an examinable part of the subject, but anyway, there's a high-level outline of the proof in the notes in case you're interested. So for the last part, what I want to look at, and it's the last thing we're going to do along these lines in this course, is look at another curious notion of subset of natural numbers, which is again a kind of set that fails to be computably enumerable in a very strong way, but a different way from being productive. And in order to motivate it, I want to observe first some, hang on, I need to put the camera in the right place. I want to observe first a property of productive sets. So we're going to have a proposition. Prop stands for proposition. If A is a subset of numbers, a set of numbers is productive, then A has an infinite computably enumerable subset. So it's not computably enumerable itself. It's necessarily an infinite set because any finite set is computable, so certainly computably enumerable. But it has the strong property, it's not just infinite, but it has a computably enumerable infinite subset. And there's a quite detailed proof in the notes, but I'm just going to give a proof outline here, which is we construct a computable function f. F is a total function with the following behavior. So f of 0 is some number e0 such that the e0 index computably enumerable subset, computably enumerable set, is the empty set. So in other words, it's some index for the everywhere undefined function. So it enjoys the property that f of 0 is like this. So f of 1 is, well, we're assuming that A is productive, so suppose G is a witness to productivity. Sounds like something from communist culture or something like this. But anyway, but we know what it means. So E0 is an index for the empty set. So if you say the empty set is of course a computably enumerable subset of A. So productivity of A. So W of E0 will be some element E1 in A, but outside of, well, obviously outside of the empty set anyway. So that F of 1 be E1. Sorry, so it's actually I want F of 1 to be E1 such that E1 is an index for the computably enumerable set, which only contains one element, which is G of E0. So that's an element of A that's outside of the empty set, because everything's outside of the empty set. F of 2 is going to be an E2, such that E2 is an index for the computably enumerable set that contains two elements, G of E0 and G of E1.
So this is a computably enumerable subset of A. So G of its index E1 by productivity is an element of A that does not belong to this set, so it's different from G of E0. So this is now a computably enumerable subset of A with two elements, E2, and if you apply G of E2, we're going to get another element of A that's outside these elements. So F of 3 is going to be E3, such that W of E of 3 is G E0, G E1, G E2. And the point is that each stage we find an index for the set that consists of all the previous elements together with what we obtained by applying G to the index for our set of previous elements. And once we've done this, then the image of G composed with F is going to be an infinite, is the set G0, G1, G2, G3, and so on, which is infinite because each G of E and N is always different from the previous elements, and they always belong to A, so which is an infinite subset of A. And computably enumerable because it's the image of a computable total function. And we had 2 weeks ago that the images of computable total functions are computably enumerable sets. And PE, because it is the image of a computable function. Okay, so the missing step in the proof is how we define the function f. It's not that hard. Essentially, you're iterating the process of finding a way of unioning the set given by an index you have already with a single additional element that you're adding to it. So you need a way of unioning a given computably enumerable set with an element. And you iterate that process sort of recursively in the natural numbers, applying primitive recursion to do that. And the details for that are in the notes. But that's the idea of how one constructs, finds this infinite computably enumerable subset. And just to remark, the corollary of this is under the same conditions, A also has an infinite computable subset. And that's by a result we had again 2 weeks ago, which is that every infinite computably enumerable set has an infinite computable subset. Okay. I'm going to write that down. So what we've got is that we have a productive set, it's not computably enumerable, but it has an infinite computably enumerable subset, and indeed an infinite computable subset. So this raises a question that's kind of natural to mathematicians, but probably not to anybody else, which is, could we potentially have an infinite set that contains no infinite computably enumerable subsets? So such a set would necessarily not be computably enumerable because it, if it were computably enumerable, it's a subset of itself. So it would have an infinite computably enumerable subset. So a set of natural numbers is called immune. I have no idea where this terminology comes from, but anyway, it's immune. It was a useful property to have in times of epidemics. I'm not sure if this is a particularly useful property to have, but so a set A is immune if it has no infinite, sorry, if it is infinite and has no infinite computably enumerable subsets.
Right, I need to change the camera.
And has no infinite C subsets. So like, it's clear such a set is not computably enumerable. And by this proposition here, it's also clear that such sets are not productive. So this is a different class of sets that are not computably enumerable in a strong way, enjoy some stronger property that implies not computably enumerable, that's disjoint from the set of constructive, the collection of constructive sets. So any immune set is clearly not computably enumerable and also not productive. And it's far from obvious that an immune set should exist. Clearly, we can't use the complement of K this time because that's productive, so it can't be immune. It's far from obvious because it's a very weird property. So we've got an infinite set, but it's infinite, but in a way that it's very hard to show that it's infinite, because remember, computably enumerable sets are the images of computable functions. That's those sets we can enumerate in a list, in an infinite list, possibly with repetitions. It's an infinite set, but there's no way of computably enumerating any infinite subset of that set. If you try to enumerate a subset of that set, you're going to get stuck in some finite subset, or you'll go out, or you go outside the set. Very weird property to have. But such sets do exist. And what we're going to end with is a result that gives an example of such a set to prove that they exist. But I'm not going to just prove that such a set exists, I'm going to prove that a slightly stronger property of a set exists, and then we're going to be done with such weird properties of sets, having achieved what we're about to do. So the slightly stronger property is, so again, this is a different way of being not a computably enumerable set in a strong way. So if we consider that that's computably enumerable whose complement that has this property, and that's a different way from the creative set we had before. It's a different way of having a set that's computably enumerable but not computable in a strong way. So again, such sets are going to have names. So a set A of natural numbers is, and now we have really, I mean, I don't know where these names come from. This was the worst choice of name ever, is simple if it is C, and its complement is immune. So, I really have absolutely no understanding of in more sense that is good. Because I haven't read the original paper. I mean, maybe the authors tried to justify it at the time. But for me, the interesting aspect of this is the idea, it's really not so much the simple property, but the immune property of the complement. The idea that you can have an infinite set that's infinite, but in this very intangible way that you have no way of writing a computer program that will list infinitely many elements from the set. And that's a very weird. That always, yeah, however many years I've known this material, it always seems like a very weird property to me. So we're going to end with the theorem that an immune set exists, but not only an immune set, but actually a simple set exists. So, yes,
The camera.
the camera again. Thank you very much. This will hopefully be the last time I need to move it. This is Close's theorem. I guess it's just an immune set exists. Sorry, a simple set exists, yeah. There exists a simple set. And in proving it, we're going to actually construct one. And you will see how simple a simple set really is. It's not actually as complicated. I mean, you know, one might be fearing the worst at this point, but it's actually not too bad. So we consider the computable function, partial function, defined as follows. F of z, I call it z in my notes. F of e is phi e of z. So that the point is it's going to pick out some element z, we're going to see what it is, but it's finding some element in the image of phi of e. But it has to be a sufficiently high element in the image of phi of e. So if z is the smallest number, such that phi e of 0, phi e of 1, all the way up to phi e of z are all defined. So phi is defined on the first z, or z plus 1 arguments, and phi e of z is sufficiently large. It's got to be greater than or equal to 2 times e. Bit of a weird condition. But the thing is, it can be found, such a z can be found using minimization, because we convert the greater than or equal to 2e in a search for some related function, search for a 0 of a related function. And because all these values are required to be defined, we can do that search using minimization. And it's undefined if no such z exists. And we define A to be the range, image of F. I always seem to switch between range and image, but I always, you know, it's the same thing, the range of a function, the image of a function. So A is the range of that function, which is compute. So A is computably enumerable because we saw 2 lectures ago that the image of a partial computable function is a computably enumerable set. Because the image of a computable partial function okay. So we've seen that A is computably enumerable, so it remains to do the difficult bit, which is to show that the complement of A is a simple, sorry, not simple,
we're showing that A is simple. The complement of A is an immune set. So we need to show that the complement of A is immune. So firstly, we need to show it's infinite, and then that it has no computably infinite subsets. But let's show that the complement of A is infinite. So to show A prime is the complement of A is infinite, so notice that whenever f of b is a number n, well, such an n must be phi of b of z, where phi of b of z is greater than or equal to 2 of v. So note that f of b is n implies that n is greater than or equal to 2 times p. So that means well, maybe I'll write out everything that's so in particular, so the numbers from 0 up to 2n minus 1 to 2n minus 1 can only appear as f of a for e less than n, strictly less than n. So that means, so not all of them will appear because f will be undefined on some of those values, but we can f of e can have at most taken out n of these numbers. There are 2n numbers here, and the image of f can contain only n of them. So at least 10 distinct elements, distinct numbers from 0 up to 2n minus 1, so there are 2n numbers there, at least n of them lie outside the range of f, so lie in the complement of A. Okay? So that means that this is true for any n, so that means that A is necessarily infinite. So the complement of A is infinite. Okay. So lastly, we need to show, and I'm afraid I do need to move the camera once more, because I don't think if I want to squeeze it onto the bottom of the board. It would almost fit, but I'd have to write rather small. No. The last thing we want to show that, well, let's keep the definitions here. So we'll go to the right-hand part of the board, and we still need to show that the complement of A contains no infinite computably enumerable subset. So we must show that A contains no infinite, complement of A contains no infinite C subset. Okay, so let B be an infinite set, an infinite computably enumerable set. We show that B
It's not a subset of the complement of A. So by a theorem 2 weeks ago, computably enumerable sets are exactly the images of computable partial functions, but they're also exactly the images of computable infinite. Infinite computably enumerable sets are exactly the images of computable total functions that have, well, every infinite computably enumerable set is the image of a computable total function. So let E be such that phi sub E is a computable total function with the image of phi sub E is B. So what we're going to have a look at is what F does on E. And then an F of B, well, F of B is defined because the image of phi sub E is infinite, so there certainly exists some value, some element of the set, some element of the image that's greater than or equal to 2e. Because it's an infinite set, so some value must be greater than or equal to 2e. So there is some z such that phi sub E of z is greater than or equal to 2 of e. Moreover, phi sub E is a total computable function. Did I say that? It was supposed to be, yeah, a computable total function. So phi sub E is defined on all the lower values. So that means that f of B is defined to be some such value. So when f of B is defined, because B is infinite. Because phi E total and B infinite. So f of B is clearly in the range of F. So I'm writing image and range, so let's say image. So f of B is in the image of F, so it belongs to A. But also f of B is in B, because f of B equals phi E of Z, the sum of Z, and B is the image of phi B. So we have an element of A intersect B, and that means that B is not a subset of the complement of A. So in other words, f of B belongs to A intersect B. That's it. B is not a subset of the complement. Moving on. So the complement of this image of F is indeed an immune set, this curious property, and moreover, because the image of F is computably enumerable, then we have a simple set. Good. Well, so I think looking back on what we've done today, you know, they're essentially the two parts. The first and third part together are abstract material, these rather strange properties of sets. And I must admit, the immune and simple sets are something of a curiosity, but you know, I think the idea of an infinite set that you can't actually enumerate any infinite subset, I think that's an intriguing idea. But the productive sets that we did in the first part, I hope that this discussion of the relationship with mathematical truth in Gödel's theorem gave you some hint of how that is actually really objectively quite an important notion. Anyway, that's the end of, we've been getting more and more abstract in this block of lectures. That's the end of that material. As I've said, from next week, we're going to start afresh and look at a new machine model, a variant of Turing machines, and look at some other development of computability theory that's not to do with computability on, there's computability on infinite objects rather than finite objects that we've been looking at so far, such as natural numbers and words. Okay, so that's everything for today. I'm going to stop the recording.